All right, this time around we're going to take a look at the conjugate of a complex number. So we'll define the conjugate and go ahead and look at several properties involving conjugates. So as always, we begin with a definition. So what is a complex conjugate? Well, the conjugate z bar, which would be our notation for the conjugate, of any z that's equal to x plus yi will be given by x minus yi. So remember, minus really just means opposite. So whatever y is for the complex number z, its conjugate will have the opposite imaginary part. So notice the real parts are exactly the same and the imaginary parts are opposites of each other. So pictorially, if this is the complex plane and you plot any complex number z, its real part will be the same, but the imaginary part will be the opposite sign. So z bar, oh whoops, got that in the wrong spot, don't I? Should at least somewhat look. So whatever this number is here, y, this will be the opposite of that number. So basically a number and its conjugate are the same distance from the origin. So they will have the same modulus. One's just reflected over the real axis. So just to see some actual examples, you could have like 2 plus 3i, and its conjugate would be 2 minus 3i. Negative I, principal square root of 6, its conjugate would be positive I, principal square root of 6. Negative 5 plus 7i, and negative 5 minus 7i would also be conjugates. So the idea is that the real part would be the same and the imaginary part would be the opposite. Okay, let's go ahead and take a look at some properties of conjugates, or properties that include conjugates. So the first property states that the conjugate of a sum would be equal to the sum of those complex numbers conjugates. Or you could think of it the other direction, that the sum of two complex numbers conjugates would be equal to the conjugate of their sum. So let's see a proof of that. Let z1 be x1 plus y1i, and z2 be x2 plus y2i. Then let's do the conjugate of their sum. So their sum, you would just add the real parts, so x1 plus x2, and add their imaginary parts. However, we want the conjugate of that, so the imaginary part has to be the opposite sign. So this would be minus. Well, let's rearrange what we have here. So we have x1 minus y1i. Then we have x2 minus y2i. And x1 minus y1i is the same thing as the conjugate of z1, and x2 minus y2i is the same thing as the conjugate of z2. So this proves that the conjugate of a sum is equal to the sum of their individual conjugates. All right, let's go look at some of the other properties involving conjugates. So we just proved a property involving the sum of two complex numbers. Well, it turns out that basic property is also true for the difference of two complex numbers, the product of two complex numbers, and the quotient of two complex numbers. So I won't do the proofs here because they're very similar to the proof we just did for the sum, and I'll probably leave those as exercises for this lesson. But let's go take a look at two more properties that involve a conjugate. So the first property states that the real part of z can be found by taking z plus its conjugate and dividing by 2. So if you ever needed just the real part of a complex number, you could find that by taking that complex number plus its conjugate and divided by 2, or the other direction. If you have this expression here, you can replace it with just the real part of z. So to see why that actually is the case, take z and add its conjugate. So this would be z, add its conjugate. You get x plus x is 2x. Those are additive inverses, so it's 0. So basically z plus z bar, or its conjugate, is equal to 2x. And if you divide by 2, x, which is the real part of z, is just z plus z bar over 2. And then we have a similar property involving the imaginary part of z. So the imaginary part of z can be found by taking z minus its conjugate and dividing by 2i. Or again, if you have this expression on the right-hand side, that can be replaced with the imaginary part of z. So it's an equal sign, so either side, either direction would work. So to convince yourself that that's actually true, take z and subtract its conjugate. So here's z, subtract its conjugate. X minus x is 0, and then you get 2yi. So basically z minus z bar is equal to 2yi. Divide by 2i, and y is the imaginary part of z. So we see that the imaginary part of z is equal to the complex number minus its conjugate divided by 2i. So now let's go take a look at a couple more properties related to conjugates. This first one states that if you take a complex number z times its conjugate, it will be equal to the modulus squared. Or the other direction, the modulus squared is the same thing as a complex number times its complement. So let's see if we can't convince ourselves that that's actually true. So if we take z times its complement, we'd have x plus yi times x minus yi. And we would get x squared minus y squared I squared, which is x squared plus y squared, and that is the same thing as the modulus squared. Now this next property states that the modulus of a product is the same as the product of two moduli. So in other words, you can multiply the two complex numbers together and then find the modulus, or you can find their moduli, I believe, separately and then multiply those together. So again, to see a quick proof, let's consider the left side squared. Well, the left side squared, according to our property right above it, because that said, the property above it told us what to do with a modulus squared. Well, here we have a modulus squared, and it's apparently equal to the product of that number z and its conjugate. So this modulus squared should be the complex number times its conjugate. That's just using the property right above it. So that would be Z1 times Z2, and we know that the conjugate of a product is the same thing as the product of the conjugates. And then a quick rearrangement. And again, using the property right above, Z1 times Z1 bar is the modulus of Z1 squared, and then the other one would be the modulus of Z2 squared. Well, we know that the modulus is positive, and these moduli are positive, so since this one squared equals these two squared, it must be true you could just take the square root of both sides of the equation. You can think of it that way. It must be true that the modulus of the product is the same thing as the product of the individual moduli, again, I believe. And then our last property is going to be similar to the one we just did, that the modulus of a quotient is the same thing as the quotient of two individual moduli, as long as you're not dividing by 0. So again, the proof would be similar to the one we just did. Again, I may leave that as an exercise for this lesson. So in our next lesson, we're going to talk about the argument of a complex number, as well as some different ways you can write a complex number. We've only actually taken a look at one way, called rectangular form, or sometimes called standard form. So we're going to talk about other ways you can represent a complex number in the next lesson.